ladies and gentlemen, it is time for us to get into our next session. We, of course, thanked Dr. Manish Gupta for his presence. So joining us for the next session is Professor Gupta, Chair in the Department of Computer Science and Engineering at the Indian Institute of Technology, Delhi. He's also the founding head of the School of Artificial Intelligence at IIT Delhi. He's also the affiliate faculty in the Department of Computer Science and Engineering at the Washington University. His research involves exploring neurosymbolic machine learning, computer vision for radiology, NLP for robotics, multilingual NLP, and several threads in intelligent information systems that include information extraction, knowledge-based completion, question answering, summarization, and dialogue systems. He was ranked the 56th most influential NLP scholar and 64th most influential AI scholar by Arnett Minor AI 2000 ranking. He's a Niti Aayog AI member, India, and served as program co-chair of AAAI 2021. So for our next session on neural models for monolingual and multilingual information extraction, we have with us Professor Mausam. While Professor joins us on the screen, just a little hygiene announcement for all the members of the audience. Members of the audience, please note you can ask Professor all your questions through the Q&A feature that we have in Zoom. And of course, we will have a 30 minutes of session and 10 minutes of Q&A. Over to you, Professor.
Thank you. You should be able to see my slides and hear me now.
Yes. We can, sir. Loud and clear.
All right. Thank you very much, Fatima, for this detailed introduction, kind introduction, and thank you very much to Huawei and ACM for thinking of me for making this presentation. I was really inspired by Manish's presentation on all the cool things that Google has been doing. But in this talk, we are going to drill down a level a little bit. So we will be focusing a little bit of our energies on one specific sub-area of AI, and that is information extraction. The reason I decided to give this particular version of the talk, in fact, this is the first time I'm giving this talk, is because Huawei itself has been kindly supporting us in this endeavor and collaborating with us. So I thought it is appropriate that some of that work comes out in this talk. Some of this work is actually unpublished and the results right off the press, but you know, so be it. Before I start, I should mention that this is not my work. Actually, I don't do any work anymore. This is really work of my PhD students. In particular, the work that I'll be showcasing is work of my PhD student, Keshav Kulluru, with a little bit of work that comes from other PhD students, Danish and Vipul, and including many other research scientists and, research engineers and undergraduate students whose names I've listed, along with senior collaborators, Somen Chakrabarti, IIT Bombay, and Parag Singla at IIT Delhi. So let me get started. I really like to start with this information overload problem that you and I are all dealing with, right? So we know that we are dealing with a lot of new information in a day. In fact, somebody believes that we deal with a lot of new information in a day that a person in their entire life in the Middle Ages. So of course, you know, genetically, we are not wired to deal with such huge, humongous inflow of information. And so it is critically important that we build intelligent systems that are allowed, that enable us to deal with all this information in a succinct manner. They give us the information that we are really looking for. And of course, there's a lot of work in this area, be it Siri, Cortana, Google Home, Alexa, or what have you. There are lots of these lovely intelligent agents that are coming in our life. And my a major focus of my research is to think about how to enable them and what all should they be able to do even if they can't do it today, right? So one of the things that of course we should be able to do is question answering, simple question answering. Like if you are interested in Big Boss and you are interested in who won the OTT Big Boss, which just concluded a few weeks back, then you ask one of these agents if they should be able to say that Divya Agarwal won this. In fact, Google itself can do this now. So it's no longer give me a query and I'll give you 10 blue links, which will have what you are looking for. It is also giving us targeted responses, but some of it happened as in response to some of the work that we had been doing at the time at University of Washington. You could ask more interesting questions. What sports teams are based in Arizona? And it should be able to give you a list of answers. You should be able to ask temporal queries like when did Asian Games occur, and it should be able to give you a list of years that this happened. Obviously, we all want to enable this in various languages. So if you say Asiai Khel Kab Kab Hue, the system should be able to give exactly the same answer. You should also, it should also make your life easier when it comes to comparing products. So comparing entities, like if you are interested in buying Amazon Fire or Roku for your to make your TV sort of more digitally savvy, you don't know which one to purchase, and you don't have the time to go and read each of Amazon's reviews. But maybe a good system should be able to give a balance pro-con analysis, saying both have good UIs. Maybe Roku works perfectly, but Fire doesn't always work very well when it is getting installed, etc., etc. So whatever, right? Mine information from reviews and compare them for a user. You should also be able to answer queries like suggest an Italian restaurant near Qutub Minar that serves excellent raviolis. It's a difficult enough query. You should be able to check whether the restaurant is Italian or not, whether its location and Qutub Minar's location are in the vicinity of each other or not, and whether it serves excellent raviolis or not, which may come from user reviews. And if a system is able to then give an answer like, okay, why don't you try the hotel or the restaurant Diva or the restaurant Perbacco, you should also be able to enable a dialogue like the user says, make a booking for Diva tonight, and the agent comes back to say, oh, how many people do you want the booking for? So you can start to see that we are really interested in enabling various kinds of targeted conversations with our information agent, one which is able to mine information from various diverse sources, possibly on the web, to give us exactly what we are looking for. And how to build such a system has been a major focus of my research. And I often like to think about it from an information systems pipeline perspective or data pipeline perspective, where the raw data, you can think of all the blocks on the floor, the whole web, and very hard to make sense of, is first converted into something like an information. And you should start to think about what does that mean in our context. But this is sort of the very standard data pipeline that people say that the raw data gets converted into what is important and what is not, the information bits, which are then organized in context of each other to create a bigger body of understanding or knowledge. And that's called knowledge. And then from knowledge comes understanding, deep understanding, and from that comes wisdom, right? And so this is the information systems pipeline. But what does it mean in our context? In our context, it may mean that like the raw data is maybe text, because I work in NLP, but it could be images, it could be audio, it could be video, but raw data is like text, and we are interested in the important bits there. So let's call them facts. Like Asian Games occurred in 2010, or Google India AI research is based out of Bangalore, things like that. And then these facts are put together in a knowledge base. They are sort of made a little bit more semantic and more normalized. And then when you have this knowledge base of world's information, then you can enable interesting applications. And today I'm going to be focused my energies on the very first part of this, right? Text to facts part. This is called information extraction. I should say that we have done a lot of work on the other side also, which I'll briefly mention towards the very end of the talk. Now, before I start talking about the various techniques that have come out of our group in the recent past, I do want to get some vocabulary going. And the traditional form of information extraction is when we are given an ontology ahead of time. So we are interested in some relations or some phenomena, some kinds of events, some kinds of relations, some vocabulary has been provided to us. And the goal of the system is to read text, like the text here, Apple's founder Steve Jobs died of cancer following a long battle, and convert this into, let's say, an information fact, which uses the vocabulary that has been given to us in the ontology. So what is the vocabulary here? Maybe that there is a relation founder of. This relation is between organizations and people. The first argument is the organization. Second argument is a person. Okay. And from there, a closed eye system would be able to extract that the previous sentence expresses a relationship founder of, which is between the entities Apple and Steve Jobs. Okay. So this is sort of what a closed eye system would do. So if it knows that there is a founder of relationship that it needs to extract, it may extract tuples like Google Larry Page and Microsoft Bill Gates. If it is given an acquisition relationship, then it may extract like Apple and Shazam or Microsoft and Maluba. The point is that it can only extract information for which it has been given a vocabulary element in the ontology. And extrapolating it, it can only extract information for which it has been given a lot of training data. So that is closed IE. It is a little bit more consistent, more semantic, but it has these limitations. On the other hand, in response to closed IE or IE in general, we have at University of Washington then and now continuing it at IIT Delhi defined the paradigm of open information extraction. The idea is that you extract information from text, but you don't limit yourself to relations in the ontology. You do it for all relations in all domains as well as you can. And right, so if you have the same sentence, Apple's founder Steve Jobs died of cancer following a long battle, an OpenAI system should be able to recognize that Steve Jobs and Apple have a relationship expressed in the sentence, and the relationship can be written down as is the founder of, even though the words is, the, or of were not present in the sentence. Notice that relation now is a textual phrase rather than an ontology element. Similarly, the same sentence also expresses a relationship between Steve Jobs and cancer, which is that Steve Jobs died of cancer. And so if you do this at scale, you start to collect lots of facts about, hundreds of thousands of relations and so on and so forth between various arguments, like Google acquired DeepMind and oranges contain vitamin C and Edison invented the phonograph. And now you can query it on the web and you can try to get answers to questions. I'll show you a quick demo in a minute or so. The good news is that it is ontology free, and that really scales things out. So in our talk today, I will be focusing on both OpenAI and closed IE. OpenAI is a piece of, a research area that has been strongly associated with me for the last several years, but we have been doing some work in traditional IE also. And I will first talk about the English technology that we have developed, and then how we are taking the multilingual leap, because eventually, and it will connect to the talk that Partha is going to give in the next segment, because he was interested in taking AI technologies to 1 billion next users. And if you do that, you really need to be multilingual. Before I start, I want to quickly give you a demo. So this is so if you ask the question, what kills bacteria? Basically, you're looking for various arguments. One, where the relation is kills and the argument 2 is bacteria. And you search on our systems, and the system actually starts to give a lot of answers, like chlorine kills bacteria. And you can start to see various sentences from where this particular fact was extracted, like chlorine is added to kill bacteria, and chlorine, a strong oxidizing chemical, is used to kill bacteria. And from here, our system was able to figure out that chlorine kills bacteria. You can see that tea tree oil also kills bacteria. Of course, it does make some mistakes also, because it says water kills bacteria, but it's actually hot water that kills bacteria. You can start to ask questions that you did not anticipate ahead of time, right? You can check what the system knows about, for example, symbols of countries. So you're looking for argument 1 and argument 2 such that the relation is symbol of, and argument 2 is of the type country. And you may not have this in ontology, but if you don't have this in ontology, and if you're interested in creating a table for this, you will have to do a lot of training data, give a lot of training data ahead of time. We don't want that, and OpenAI sort of responds to that. So you can start to see that elephant is a symbol of Thailand, and kiwi is a symbol of New Zealand, and so on and so forth, right? So you can, this is collecting information from diverse sources at different points and aggregating them to show a clean view to a user. And this is one of the ways in which we can do information summarization. Of course, more things need to be done if you want to answer queries and questions and dialogue that I detailed early on. Now, open information extraction has had a long history. It started in 2007, as I said, at University of Washington. And right from 2010 onwards and OpenAI 2 onwards, I have been involved in this project. And when I came back to India, we continued to develop this in IIT Delhi. And in the last 5-6 years, a lot of the OpenAI innovations have come from India and from IIT Delhi. I want to briefly talk about the deep neural model leap that we took in the last year or two. So basically, we have now released OpenAI 6, which has lots of deep neural models built in. Okay. So let's get started. Apple's founder Steve Jobs died of cancer following a long battle, and we want to extract these particular extractions. So basically, we want to build an OpenAI system which will take in a sentence and output these extractions. Pretty straightforward, should not be very hard, right? And the neural models can do a lot of cool stuff today, so this should be a piece of cake. And if you are following the literature on NLP, you can start to quickly see that this looks like a sequence-to-sequence model and an encoder-decoder model, where you have to encode the input, the sentence, and decode the output, the set of extractions. Now, so far so good, but there is a challenge. What's the challenge? The challenge is that the output space looks like a set of extractions. Now, we know how to output a sequence of words, but how do we output a set of words? In fact, technically, we have to output a sequence of tokens, right? Because each extraction is a sequence of tokens, but various extractions form a set. And so there were some choices that we needed to make, right? For example, how to output a set, right? So if I ask you to, write down a set of colors, right? You will still write it out in some order, even though the set is an order invariant construct. If you are outputting a set, like you will say red, blue, green, or you may say red, green, blue, or you may say black, blue, white. But the point is that you will write down this set in some order. There is no other way. You cannot output a set. You always have to output a sequence. And so once we realized that, we said, okay, fine, it doesn't matter. We will output a set by outputting one extraction at a time, like a sequence. Okay, so far so good. Then the next question was, how do we train large output lengths? Because each extraction itself is several tokens. But then when you concatenate all the extractions, that becomes a really large output. And you don't really have models which can do a good job on large output lengths, at least at the time. Now, of course, we know that GPT-3 can start to do a better job, but GPT-3 is not easily available. And even that starts to make some mistakes for large outputs. And so we said, okay, we will train a model which will only output one extraction at a time, right? But if it is training a model which is only outputting one extraction at a time, then we need to ensure that the model doesn't start stuttering. It doesn't just keep repeating the same extraction over and over and over. And so basically to solve that, we started giving all the previous extractions that we have outputted so far as input when we are generating the next extraction. Right, so everything else is just a formulation of these basic ideas. So you have a BERT encoder. So let's just see. This is my inputs. Apple's founder Steve Jobs died of cancer. There are some tokens which are BERT specific, which we'll not get into. We pass it through BERT. I hope you know what BERT is. BERT is pre-trained language model. In this case, trained by Google, but there are many, many language models that have come out from various sources now. These are very large models trained on humongous amounts of data and can give you what is called contextual word embeddings, which basically means that every word has now an embedding, which is in the context of the sentence that it is in. Once we get these contextual word embeddings, we can give this to a decoder. A decoder is like an LSTM, or it can also be a transformer, which is another model, a machine learning model, and it will generate one word at a time and slowly complete the output that we want. In this case, the extraction that will generate is arg1, Steve Jobs, relation is the founder of arg2, Apple. Right? But now we want to extract, so this is my second extraction now, and so I have already extracted the first extraction, and so we will give the first extraction as input to BERT, right? And so now my input becomes this large thing where first you have the sentence, and then you have the next extraction, and now you get contextualized word embeddings. And this allows me to reduce redundancy and do a small generation sequence per decoder. So now my system may generate Steve Jobs died of cancer. And at some point, my system may say, no, I have generated all the extractions I wanted to generate. You can stop. So this is the emoji architecture. The input is the original sentence concatenated with all the extractions so far, say I-1 extractions, and the out decoder is extracting the next extraction. And when we compared this, this was a paper last year, when we compared this to existing neural method, which is the RNN-OI, we had much better performance. But unfortunately, this is really, really slow. It was only able to process 2.5 sentences a second, whereas RNN-OI was able to process 150 sentences a second. So obviously, we don't want such a slow system because otherwise, it will take a huge amount of processing, right? We'll need 75 more machines or 75 more GPU cards. They will be very expensive. So clearly there's a trade-off between speed and accuracy. Emojis are several points better than RNNOI in accuracy, but 60x slower. And so we had to do better. I should point out that anything we do in our group, all the data and all the code is typically released. In this case, this has already been looked at and downloaded 3,500 times. So now, how do we fix this speed problem? And again, this is work by Keshav, and he recognized that sequence labeling can be really fast. We don't have to do generation. And in fact, because we are extracting a relation and most of the words of the relation come from the sentence itself, we can take a tagging view, and then there are typical words that we add like is or from, and we can add that in the input too. And so the first extraction is like Steve Jobs is the founder of Apple, because you can see that Steve Jobs is labeled arg1, arg2 is Apple, and is founder of can be constructed based on this tagging of a value. You have to do some reordering, but that is relatively straightforward. And so once he recognized this, he was able to create a grid labeling architecture, which avoided re-encoding due to BERT every time, which made the speed. So again, the system is that you give the sentence, you pass it through BERT, you then run it through a two-layer transformer, which is a machine learning model, and that gives you sequence labeling. So it gives you a label for every word, which is equivalent to generating extraction. But then the cool thing he did was that he took this labeling and he converted it into some embedding and concatenated it with the embeddings, which were the output of the two-layer transformer. So that way, the second extraction is kind of aware of the first extraction. Right? And when he did that, the good news was that he was not re-encoding through BERT every time for every extraction, and that made it much faster. Okay, so this is sort of how the iterative grids look like. So the first extraction is Steve Jobs, the founder of Apple. The second extraction is Steve Jobs died of cancer. There is no third extraction, so that will be all none, and that would mean that we can stop. Now, the good news now was that this new system IGL was pretty much same in performance in terms of speed, and it was even better than RNNOI, but it was worse than emoji, because emoji had the generation. Generation is obviously more capable in terms of capacity or so on, and so more expressive, and so it was doing better on the quality. And that's where he added one other very nice insight. He realized that when he looked at the quality of the output of the labeling model, he recognized that he was missing some recall, right? And he needed to cover more of the sentence. And to cover more of the sentence, we drew on from another PhD student that I have, Yatin Nandwani, who had a very nice paper in UREPS a couple of years back about adding constraints in machine learning models. So let's look at a quick example. So if there's a sentence, Obama gained popularity after Oprah endorsed him for the presidency. And if OpenAI extracts Obama gained popularity, it's okay, but not great. If the system also extracts Oprah endorsed him, that's okay. But again, that's limited because we are missing the words for the presidency. Instead, if the extraction is Oprah endorsed him for the presidency, then we are covering more of the sentence, right? So what is changing is that we are trying to cover more of the important words in the sentence. And we added that as additional constraints into the machine learning model as auxiliary losses using the methodology that Yatin had developed for the UREPS paper. And when we did that, we were able to get a much higher performance and also at the same speed. So this was a paper that was published last year at NLP, and this is called constrained iterative grid labeling. It has slightly better performance than emoji, but it is 60x faster than emoji and almost at par with RNNOI. That really solves the whole thing. And so we have released this as an OpenAI 6 system. It has already been downloaded more than 1,500 times, and you are encouraged to have a look at it if you are interested in this kind of stuff. Now, going forward, we were very interested in seeing how this technology can be applied to various other languages. And there was a real challenge. What was the challenge? The challenge was that OpenAI has already been focusing on English and primarily on English. There were a few researchers in Chinese and one in Portuguese and a couple in German and so on. But it has not had the kind of focus energy that is needed to really build a system which is high enough quality to be usable, as we have been able to do in English. So how do we extend OpenAI in English to other languages seamlessly, right? And we don't want to do one language at a time. That's very slow. We really want to scale it up to many, many, many languages at once. And the biggest challenge was training data, right? So, we can train a big neural model, but for that, we need a lot of training data. We have some tricks and of the trade to do it in English. How do we do it in general? And manual annotation is obviously very expensive. And so we realized, why don't we just translate English data to create training data for a new language? And if we can do this right, then we can really scale to all languages at once. Now, this sounded like a good idea, but there were some challenges. Okay, and I will show these challenges with a very simple toy example. So, imagine the sentence, the shield of Athena Parthenos, sculpted by Phidias, depicts the fallen Amazon. From here, English OpenAI training data has the extraction, the shield of Athena Parthenos depicts a fallen Amazon. Seems innocuous. Now, suppose we want to create a training data for Spanish. So we first take a machine translation system like Google Translate. We convert it into the original English sentence into Spanish. So far, so good. El escudo de Athena Parthenos, sculptado por Phidias, representa un Amazonas falecido. So far, so good. Now you have the extraction. The shield of Athena Parthenos depicts the fallen Amazon. You can actually serialize it a little bit better, forget the relational argument structure, and you can almost read it like a sentence. In this case, you can exactly read it like a sentence. So you make a sentence from this extraction, and again, you pass it through a machine translation system independently, and it gives you an independent sentence. And now you sort of do some kind of projection. So you say, this was the original extraction in English. This is the translation in Spanish. Let me recreate the original structure of argument, relation, argument, and this gives me a relation which is equivalent to this. And you can hope that this is going to make a good training data for you. So what is the training data? The Spanish sentence, which is translation of English sentence, and Spanish extraction, which is the translation of English extraction. Because these are unfortunately independent machine translations, there can be inconsistencies. For example, the original sentence has the word falecido, and the Spanish translation has the word caído. And I am told that both caído and falecido are synonymous and equivalent in this context. But to create a translation system, not a translation system, sorry, to create an OpenAI training data where the extraction should be outputted from the input sentence, this is not ideal, because we are really asking the model to now output synonyms or equivalent expressions or even inconsistencies, something that you don't want the machine learning model to learn because your data is noisy. So we want to fix this problem. And so we created a better pipeline called alignment augmented consistent translation, where everything else up to this point remains the same. But then we take the sentence in English and sentence in Spanish and do some alignment. So this automated alignment tells me that the in English is equivalent to el in Spanish, and shield is equivalent to escudo, and fallen is equivalent to falecido. And so now we give these alignments when we are trying to do translation of the extraction. So now what happens is that you are sort of encouraging the model to use these words which are in the alignment when they are generating the Spanish translation. So there it would be incentivized to not use the word caído and in fact use the word falecido, because it is given as input, additional input, which is the alignment. And so once we do this, we are able to create a much cleaner training data in Spanish. And then we can train a neural model. And this is what we have done. We have submitted this paper recently and has good reviews. We did experiments in 5 languages: Spanish, Portuguese, Chinese, Hindi, and Telugu. And we were able to find an improvement of up to 20% F1 score, with 10% area under the precision recall curve over various pre-existing multilingual models that were existing, right? So pretty good stuff as far as I'm concerned. And it has been able to show that, multilingual OpenAI has a lot of hope if we are starting to generate training data automatically. Without going too much into the detail, we have been using OpenAI in a lot of diverse scenarios. And I will not get into that too much, but just to say that even for people at large, this is very helpful. So this is a application we built for DARPA a few years ago, where the DARPA was interested in, for example, this person who may be a terrorist, right? And so once we showed various OpenAI extractions about this terrorist, in a very, like, even if you stare at it for a minute or 30 seconds, you will quickly know that, yes, indeed, this person is a terrorist because this is an operative of Al-Qaeda, military chief, strategic planner, military commander of Al-Qaeda. He has married somebody's eldest daughter, which may or may not be relevant to you. He has been apprehended by Iranian authorities. He has been FBI's list of most wanted terrorists, etc., etc. So instead of going into the original text documents and reading a lot of information about this person, which might be time consuming, OpenAI was able to summarize and distill down a lot of useful information for you. We have not been the only set of people thinking about this particular usefulness. People in scientific literature have been thinking about how do the diseases connect, and they use OpenAI paths. For example, on the left is Alzheimer's disease, on the right is Huntington's disease, and they were able to show that Alzheimer's is the common cause of cognitive impairment, which is also an early symptom of Huntington's. So they have both cognitive impairment as symptoms and things like that. So they were able to relate diseases by using OpenAI. One of my students, Danish Contractor, has been able to put together comparisons of entities using OpenAI phrases. In the interest of time, I will skip the various applications that OpenAI has, and I will just briefly talk about some of the very, very latest work in closed-eye. This is really work that has been done in the last month and a half. So, this is not published anywhere, and you can think of it as a sneak peek of what is about to come from our group. One of the, again, major challenges in closed-eye is where do we get training data from? And so people have developed this paradigm called distant supervision. The idea is that you may have some knowledge base like Freebase or whatever, which gives you maybe information about various relations, like in this case, relation of birth location. So you know that Barack Obama has birth location Honolulu, Mitt Romney has Detroit, Albert Einstein has Ulm, and so on and so forth. And now you go on the web or you go into a corpus and you search for sentences which have both Barack Obama and Honolulu, or both Albert Einstein and Ulm. And you make a bag out of it, right? So this bag contains sentences which do express the birth location relationship, like he was born in Honolulu, but also sentences which do not express the birth location, like birth notices for Barack Obama were published in the Honolulu Advisor, but that does not mean that he was born in Honolulu, right? And so we call this a bag. So these are the bag of sentences which represent both entity 1 and entity 2. We don't know which ones represent actually the relation, but this is what we need to do. This is a weak supervision. We need to use this supervision to train an extractor, which now, given a new bag, can predict whether the relation holds between this pair of entities or not. And there are lots of recent architectures on this. They encode each sentence in the bag separately, and then they use intra-bag attention over sentence encodings to generate bag embeddings, and then they decode the bag embedding into the relation. Okay, I'm not showing you a pictorial view. We don't have that much time, but I will talk about our contribution, which is what we call bag as passage attention. Okay, so the idea is that you have a bag of sentences. Instead of encoding each sentence separately, let us make a passage out. Think of it as a sentence after sentence after sentence written like a passage. And we then give this to a contextual embedding generator like BERT, and that gives us a set of contextual embeddings for each word in each sentence. And then we kind of do relation attention. So we are interested in the relation R. So we will attend these embeddings with relation R. So that will tell us which word is maybe more important, which is less important, whatnot. And then we will aggregate it into a bag embedding, passage embedding, which is equivalent to bag embedding, which will then be decoded into whether this particular relation exists in this bag or not. And this seems like a very, very simple idea. In fact, this is maybe even a simpler idea than many of the previous algorithms or models that have been published. And we were very surprised to find that this simple idea is giving us a much better performance across the board. So the black thing is ours, word plus passage attention. And these are the various other models like CIL and so on. In fact, I think the reside comes from Partha's group at IISc, and you can see that word plus passage attention is doing much better on this NYT data set, much better on this another NYT data set. And so, we are still working on writing a paper, but we are pretty excited about this simple baseline. And then we are taking the multilingual leap also. But the bigger challenge is, where do we get the data from again? So this is a general theme in NLP, by the way. Where do we get the data from? That's the biggest challenge. And so the first thing we did was to actually create a data set. It is of 1.8 million sentences with 37 relation types in English, French, Spanish, and German. And on this data set, we have now run a multilingual bag as passage attention. And we are finding that this multilingual BERT with passage attention is also giving like really massive improvements on all existing models. So we are really hopeful that this multilingual relation extraction is going to take off in the years to come. So I'm sort of royally out of time. So this is my time to stop. As a high level, I sort of shared with you the work on open information extraction, which uses pre-trained language models with some human priors to create both fast and accurate models. Human priors improve accuracy, and the use of labeling techniques make them fast. We then took the leap to multilingual OpenAI, which auto-generated consistent training data using constrained machine translation. We then talked about closed IE, and we presented, or at least briefly mentioned, a very strong baseline using bag as passage attention. And then we are also taking the leap on multilingual closed IE, where we have shared a new data set and a strong baseline to take the research forward. I should say that, just by virtue of where I sit, we have a talk by Google in the previous segment, and the talk by Google in the next segment, and a lot of my work used BERT, which is a model that came out of Google. Also, the reason I presented this is that the work on closed IE and multilingual closed IE specifically has been heavily subsidized by or collaborated with Huawei researchers, and so I'm really thankful for their contributions. I should say that my research area is this is how a lot of the intelligent information systems work looks like. We have done a lot of work on knowledge-based completion. My PhD student Prachi is graduating this year. We have done a lot of work on question answering. My PhD student Danish Contractor from IBM is graduating this year. A lot of work is in dialogue systems. My PhD student again from IBM, Dinesh Raghu, is graduating this year. And a lot of work is in extraction, which I presented. This is work by Keshav Kolludu. And believe it or not, even he is graduating this year. So really, I have 4 or 5 PhD students, one in machine learning, who are graduating this year, and they're on the job market. And I mention this because you may be interested in them. They are amazing people. People in IBM may not be in job market, but who knows. I thank all the various funding agencies which helped me in making this research possible. And if there is any time, I can take questions. Oh, just before I finish, 2 shameless plugs. I have an NPTEL course on AI. This year, 40,000 students were enrolled in it. If you're interested in learning about what's happening in the field of AI, you're welcome to check it out. I also have a plug on School of AI. School of AI is a new entity that has been started at IIT Delhi. And we have started a PhD program, and we got lots of amazing students last year in AI. And the cycle is coming up in the next month or so. So if you're interested in doing a PhD or part-time PhD in AI, you must consider a School of AI as one of the possibilities. And we are also starting an MTech program, and the MTech program is going to start in July 2022. The press release just came out maybe today or yesterday. And if you're interested in the master's in AI, again, you should consider this. So this is something I just wanted to bring up. Thank you.
Thank you, Professor Mausam. That was a very engaging talk. We have a lot of questions, but for the interest of time, I'll ask just one question, which is the first question that came up. What is the future prospect of multilingual embedding in industries? And I would make it a bit more complex. I would also add that multilingual in a way of like a mix of 2 languages coming together, like English. How does it work?
Absolutely. So first of all, this is a heavily researched area, but there's a lot of scope. So if you look at the latest developments in the field of multilingual NLP, you would find that a lot of pre-trained language models are now multilingual. So even we use what is called MBERT, which is a multilingual BERT. I believe it has 25 languages in it. There is something called MT5, which is multilingual T5, which I believe has 100 languages in it, different groups. So I think one of them comes from Facebook, one of them comes from Google. People have been training these very large multilingual language models. And the hope is that if not to 7,000 languages, which is a really big deal, which is, I think, what the we can all hope to get someday, but probably unlikely, because it is even said that there are 2 dying languages every month. So, the languages are really, really reducing. But definitely to the next 100 or maybe to the next 500 languages, there is a lot of activity. And I expect that in the next 5 to 10 years, we would have done a lot of the important work in making our models multilingual. In fact, the next talk by Partha is going to be exactly on this topic. The other thing that you mentioned is English. And this is in the technical term for it in the NLP world is what is called code switching or code mixing. Think of each language as code. So you are writing in one code and you suddenly switch to the other code. This is going to be really important for bilingual speakers like us in India. And I would say that some of the experts on English, for example, is Manojit Chaudhary at Microsoft Research. And you should check out his work. Again, there is more work to be done, but there are a lot of interesting ideas and interesting data sets and models that are coming out. The multilingual pre-trained language models give you a lot of hope, because since they understand many languages at once, there is more hope that they can even understand a code mixed language. But I have to check what is the latest research on the use of multilingual pre-trained models for code switching NLP.
Thank you, Professor Mausam. Over to you, Anvit.
Thank you so much, Professor Mausam. That was absolutely a very, very informative talk. And thank you for sparing the time and sharing light on this amazing topic. And we really appreciate you taking the time being here.
Thank you.